Hello, 127 students. This is a video getting into the topic of quantum mechanics. It's something that we'll be investigating in the next couple weeks of class. So we've talked about light in class, and we know that light exists as waves. We can draw a wave here. And the wavelength of that light would be the distance between two peaks or two identical parts of the light. We measure wavelength in meters, and we give it the symbol of lambda in our equations. So let's think about our classroom. I'm just going to draw these representing the two different walls of our classroom, left and right. And let's say here on the left side, there's something emitting different types of electromagnetic light, electromagnetic radiation. So it might emit visible light first, and there will be a certain number of wavelengths of visible light as it travels from one side of the classroom to the other. We talked about the electromagnetic spectrum of all the different kinds of electromagnetic radiation. One kind is radio waves. So they have a very long wavelength. So I'll write here long wavelength. Then on the opposite end of the electromagnetic spectrum, we have different types of electromagnetic radiation that have very short wavelengths. And I'll just pick one like X-rays. So it would have a very short wavelength. So you can see for the same amount of distance, we have different numbers of wavelengths of these different types of electromagnetic radiation. So we have these different types of electromagnetic radiation. We use them for all different kinds of things, but they are all similar in one way, in that they all have the same speed. So all electromagnetic radiation travels at the speed of light, which we give the symbol c. And you can see the speed of light down here. So it's about 3 times 10 to the 8th meters per second. So no matter how long or short its wavelengths are, it will travel at that speed. So this is where the idea of frequency comes in. Frequency is then the number of wavelengths per second. And you can see down here, frequency is then measured in wavelengths per second, but we just shortened that to inverse seconds. And that seconds minus 1 is also equal to the unit hertz, which I'll use more often. So frequency and wavelength and light and the speed of light are all related. So something with radio waves that have this very long wavelength will also have a very low frequency, low V. That's a symbol for frequency in equations. That there's only going to be a few wavelengths per some unit of time. Something like X-rays with a very short frequency or short wavelength are going to have a very high frequency. There's going to be many, many wavelengths for the same unit of time. So wavelength and frequency and the speed of light are all related through an equation. The speed of light, c, is equal to the wavelength multiplied by the frequency here. So the frequency, we already talked about its units. The speed of light is in meters per second. So our wavelength here does need to be in meters. This is something that people sometimes forget. They use nanometers or some other unit. But for this relationship to hold true with the speed of light in meters per second, we need our wavelength in meters too. Okay, so this theory of light and how its wavelength and frequency are related to the speed of light was discovered and describes many different aspects of light. But around the turn of the 20th century, Einstein, Max Planck, and many other scientists had discovered some other properties of light that this theory needed a little bit of adding on to it to describe those new observations. And one piece of this theory that we're going to talk about in class is that light exists as waves, but also as particles, particles of energy. And those particles, the energy of light, are called photons. We don't talk about them as having any kind of mass. They don't weigh anything, but they are particles of energy here. And another property of these photons that we're going to talk about in class is that the energy of light, the energy of a photon, is based on the frequency of the light. So here we have an equation for the energy of a photon. So that's what this P is standing for. It's related to the frequency, and it's related through this constant called Planck's constant, named for discoverer Max Planck. And you can see that here, and it's also present on your equation sheet. So this Planck's constant is in units of joules per, or joule seconds. Frequency is in the units of seconds minus 1, so our energy is going to be also in the units of joules. So this relationship between frequency and energy is here in this new equation, although frequency is still related to wavelength. So if we were to solve for frequency, it would be the speed of light over wavelength, and we can substitute that also in this equation and come up with a direct relationship between the energy and energy and wavelength here, related by Planck's constant, the speed of light, and the wavelength in meters. Okay, so now we can do a little bit of practice with these different equations and these different relationships between frequency and energy and wavelength. So here we have a particular light source. It's a UV light source, and it has a particular wavelength, 340 nanometers. We want to determine the energy of a photon from this light source, and also then the energy of a whole mole of photons. So whenever we're talking about wavelength, we need to have the units in meters, so we can first convert this into meters. Times 10 to the negative 7th meters. Okay, so we want to determine the energy of a photon, and that is related to Planck's constant, the speed of light, and the wavelength in meters. So we can determine that from the constants that we know and this meters wavelength that we just converted into meters. 6.626 times 10 to the negative 34th joule seconds, and then the speed of light in meters per second, and then our wavelength. In meters. So we have seconds canceling out here in the numerator, we have meters canceling out, and we get our energy in joules, which works out to be 5.8426 times 10 to the negative 19th joules. So this is the energy that we calculated from wavelength, and this is the energy of one photon. So that's always what this equation is using, the energy of one photon. And now we need to get to the energy of 1 mole of photons. So that's going to end up being joules per mole. So what we want to do down here is cancel out photons and then have moles somehow in the denominator. So we want to get moles And we know that for every mole, there's going to be Avogadro's number of particles. And we can apply that to photons too. So 6.022 times 10 to the 23rd photons are in 1 mole. And I might write at the very top, I'm running out of room, that we have 3.5184 times 10 to the 5th joules per mole. Okay, now we can do one more kind of question like this. So now we have a light source and we know exactly how many photons were emitted from there. And we know the total energy that was emitted from that light source for all of those different photons. So we need to get to the energy of one photon and then determine from there the wavelength and the frequency. So what we're wanting to get is joules per photon. So we have 2 joules, and that is spread equally among these numbers of photons. And then if you like, you can set up a proportion, some x number of joules per 1 photon. And then this works out to be, I believe, 4.64 times 10 to the negative 19th joules per 1 photon. Okay, so now that we have that, we can then determine the wavelength and frequency. So what we know is the energy of a photon is related to Planck's constant and the speed of light over the wavelength. So I'm just going to start from here because it asks for the wavelength first, so that's what I'll do first. But there's more than one way to get to now the wavelength and frequency, and all ways will give you the same answer as long as they're done correctly with the appropriate units. So we can first then solve for wavelength. And if we plug in the constants that we know and the joules per photon that we just determined, we can determine the wavelength, which is 4.28 times 10 to the negative 7th meters, or 428 nanometers. So now we've determined the wavelength, and we just have one more thing to do, the frequency. So I'm just going to determine this using the speed of light is equal to the wavelength times frequency. So the speed of light divided by wavelength will give us the frequency. So using the wavelength we just found, and then rounding to our 3 sig figs, we get 7.00 times 10 to the 14th hertz, or inverse seconds. Okay, so now we've practiced converting between the different quantities of energy in joules, the wavelength and frequency of photons with a certain amount of joules, and then actually number of photons and moles as well. So now we can bring in one more thing, and that is energy per time. So energy per time is given in a unit that you probably have heard of before called watts. And this is in the units of joules per second. This is something that many electronic devices or appliances have a certain amount of watts listed as to how much energy they use. So what we have now is a typical microwave oven that will emit 1,000 watts, and we also know it emits a certain number of photons per second. And what we're looking for is the wavelength of the microwave rays that are being emitted by this appliance. So what we're looking for is a wavelength. So the wavelength and frequency are things that we need to determine for one particular photon. So something like energy does have an additive property. The energy of photons can be added together to give us a total energy, like in watts. But something like wavelength or frequency is not an additive property. Each wave, each photon has a particular wavelength or frequency that is not an additive thing. So right now, what we have is something in joules per second, and we know we're finally looking for our answer in wavelength. So we need to get to something in between, some intermediate step, and that is going to be joules per photon, the energy of one photon. And from there, that's what we did on the previous slide to calculate then wavelength. So what we have now is 1000 watts, and I did put this period in place behind the last zero to indicate that there's 4 significant figures in this value. So that's equal to 1000 joules per second. And we know our intermediate step we need is joules per photon. So then we can go from joules, we want to get photons down here. We know that they're 1 second will emit 7.55 times 10 to the 26th photons. So then this works out to be 1.324, if I can read my handwriting correctly, times 10 to the negative 24th joules per photon. So this would be the energy of one single photon. Okay, so now we can go from here directly into the wavelength, because we know that wavelength is related to the energy and also related to the energy through Planck's constant and the speed of light. So when we plug in the different values we know, we can get to a wavelength of 1.4998 meters. Now we need to convert this into centimeters and then get to 3 significant figures, so we end up getting 15.0 centimeters for our wavelength. Okay, so we've looked at different calculations we can do with photons in the different types of electromagnetic radiation, how to relate wavelength, frequency, energy, number of photons, and now energy per time. So for the different types of electromagnetic radiation, we talked mostly about visible light and how it relates to dye molecules. So we know that dye molecules would absorb certain colors of visible light. So these dye molecules are actually composed of many different types of atoms, sometimes hundreds of atoms. And we want to now discover what is going on with just one atom. So we know that atoms can actually absorb and then emit this energy, and it's in particular the electrons inside an atom. And when electrons absorb energy, they emit it later, and they emit that energy as electromagnetic radiation. Which we'll see in class, the visible light that can be emitted by different atoms. So it's the electrons that are doing this, and I want to draw an energy diagram for an electron. So here we have the different energy levels. And at the very bottom of our energy level, we have maybe an electron. An electron at the lowest energy level is called ground state. Or the resting state. And as you can see, electrons always have a certain quantity of energy associated with them. So this is now called a quantum, or a quantum number. And the very lowest energy that an electron can have is called a quantum number of 1. And for n, we just mean this to be the quantum number is equal to 1 at the ground state. So this electron may be able to then absorb some energy to get to a different quantum number. And I'll just call this a quantum number of 2 at the next highest quantum number. So this would be absorption. The absorption of energy by an electron. It's still bound to the atom, and the electron is now at this higher quantum state, this higher energy level. However, this electron can't stay here forever. It's actually going to stay there for much less than 1 second before it then emits this energy and it goes back down to some lower energy level. So this is going to emit this energy in the form of a photon of electromagnetic radiation. So this is the emission of a photon. And here, the emission of the photon, we can detect this, and we know that photons have a particular energy, particular wavelength, and that energy of that photon is equal to that change in energy of the electron. Okay, so this is for just an atom in general. So let's talk about our simplest atom, hydrogen. Let's begin with that. So again, we have a energy level. We have a low level, the lowest level possible. And the electron in a hydrogen atom can go to one of 6 different possible energy levels. So these are the different possible energy levels for hydrogen, and I've drawn them relative to each other. So you can see there's a big gap between the ground state, n equals 1, and the next highest state, n equals 2, and then the difference between the energy levels gets smaller and smaller as you go up to the different quantum levels. So here, let's say we have an electron that's starting in the ground state. So it can absorb as much energy as is provided to get it to some other quantum state. So the electron can skip energy levels if it's given enough energy. So let's say this electron has absorbed enough energy to get up to n equals 5, and that maybe an electron in some other hydrogen atom absorbs a little bit less energy, and it can get up to n equals 3. So those would be different absorption events. So likewise, when an electron is going down in energy level, it can skip a level. So here, this one at n equals 5, it may emit enough energy to go down to n equals 3, and it would emit a photon where the energy of that photon is equal to the change in energy of electron. Okay, so hydrogen is the most simple atom. It has just 1 proton and 1 electron, no neutrons even. So this hydrogen atom and its electron transitions are actually this is the only atom that we have been able to mathematically describe the different transitions that can happen for its electron and then the energy of the resulting photons. So the simplest atom is now described in the Rydberg equation. So here, this is relating to the emission of photons of different types of electromagnetic radiation from the different transition levels of the quantum states in hydrogen. So here we have the wavelength of the emitted light, that's in meters. Another part of this equation is the number of protons, which will be 1 for hydrogen. They're also related to quantum numbers through something called the Rydberg constant here, and this is in the units of meters. You'll find this on your equation sheet. And then we have the different quantum numbers here, the 1, 2, 3, 4, 5, 6, whatever they happen to be. So here we have the final quantum number, which will be the smaller quantum number in emission, and then we have the initial quantum number, which is going to be some larger quantum number, whatever the electron started out as. So this is relating the wavelength of the emitted light, and this is particular for emission of light. So we can also rearrange this equation a little bit to discover what is going on with the either absorption or emission of light. So this is another version of the Rydberg equation that's just been rearranged. So it is measuring the different types of the different level of energy that has occurred in the hydrogen atom. And here we have also the number of protons. Now we have a different version of the Rydberg constant, and this equation has been rearranged to have energy. So now the Rydberg constant is in the form of joules. So make note of those two different versions of the Rydberg constant. They're on your equation sheet. And then we also have the final and initial quantum numbers for the transitions of the electron and hydrogen, or the other atom we might be talking about. So here this is describing the change in energy state. If we have some emission event, then the electron is losing energy and we get a negative change in energy. If we have an electron absorbing or gaining energy, then we'll have some positive change in energy. And we'll want to use the absolute value if we're using that energy to then go on and calculate something like wavelength or frequency. Okay, so let's practice using these equations a little bit. So here a hydrogen atom is excited from the ground state to n equals 3. So if we were to draw the different levels of hydrogen, 1, 2, 3, 4, 5, and 6, we know that an electron is going from the ground state 1 to 3. So that's the transition that's occurring here. And we're looking for the amount of energy that that hydrogen electron has absorbed. So we know we'll want to use the equation, the form of the Rydberg equation relating energy. So that is the change in energy, the negative of z squared, number of protons, the Rydberg constant in the form of joules, and then 1 over the final quantum number and the initial quantum number. So we can begin to input those variables that we know. Change in energy is 1 squared for hydrogen atom, then the Rydberg constant in the form of joules, and then our quantum numbers, the final quantum number would be 3, and the initial is going to be 1. So we can start to simplify this equation. And then this quantity, the 1 over 9 minus 1, works out to be negative 0.8 repeating. So we multiply these together and we get a positive answer, which we expect for an absorption event, gaining of energy, which works out to be 1.938 times 10 to the negative 18th joules. So that's the amount of energy that it took for an electron to get from quantum level 1 to quantum level 3. That's the energy that was absorbed by this hydrogen atom electron. Okay, we have one more question that I wanted to give an example for. So in this case, we have a hydrogen atom. It has emitted a photon, and we know its wavelength. And we know that hydrogen atom electron was relaxing to n equals 2. So that was the final quantum value for that electron. It started out at some initial higher quantum level. So since we have a wavelength, we can use the form of the Rydberg equation that involves wavelengths. So 1 over the wavelength involves the number of protons, the Rydberg constant in the form of meters, and then 1 over n1 squared, the initial quantum value, or the lower quantum value, the final quantum value, and 1 over n2 squared, which will be the higher or the initial quantum value. So we can go ahead and plug in the values that we know. We need our wavelength in meters, so I'll go ahead and put in our wavelength in the form of meters. Then number of protons is 1. The Rydberg constant in the form of meters, 1.097 times 10 to the 7th meters. And then our final quantum number, or the smaller quantum number, is 2. And then our other quantum number is unknown. Okay, so I like to simplify everything outside of the quantum number parentheses first. So for this, on the left side of the equal sign, I just do that division and get 2.057 times 10 to the 6th equals the 1.097 times 10 to the 7th. Okay, then I would just divide by this Rydberg constant, do that division, and I'll pick it up here on the next slide. That division gives us 0.1875. And then subtract 0.25 from each side. This gives us a negative 0.06, which is equal to a negative 1 over the quantum number squared. So because each side has a minus sign, we can discount those and just work with positive values. And now we can take 1 divided by both sides of the equation. This 1 divided by the 0.06 decimal gives us 16.01 is equal to the other quantum number squared. So we can take the square root and get 4. So this is going to be the initial quantum number. So we know that the final quantum number was 2, so this particular electron in hydrogen was going from the 4th level down to the 2nd quantum level, and it emitted that photon of the 486.1 nanometers. Okay, so this is the end of video 2. Thanks for watching. I'll see you in class.